just classical fields, which we've sort of generally been labeling in the following way, just meaning some generic fields. And there's a few things I just want to stress again. I said them yesterday. I'm just going to keep reminding you because it's really important to stress this difference between quantum mechanics and quantum field theory. So the first thing is that the dynamical degrees of freedom are the values of phi at every single point. Okay? That's what we're interested in. And phi is something real. You know, it's something physical. You could think of it as temperature in certain cases. It's going to be a little more abstract than that when we come to quantize it. But you know, it's something that you could measure its value at every single point in space. Okay, that's the dynamical object. The guy x here is just a label which tells you which dynamical degree of freedom you're interested in. Is it the value of the field at this point in space, or the value of the field at this point in space, and so on. Okay, it's important to stress this because it's really a change from what you're used to in quantum mechanics. In quantum mechanics, the dynamical degree of freedom is the position of the particle. That position gets changed into an operator. Here, x is not going to be changed into an operator at all. It's always just going to stay a label. Okay? The second thing to stress is that, as we've seen, this guy phi sometimes obeys equations which look like equations you've seen before. Schrodinger equations, Klein-Gordon equations. But phi never has the interpretation of a wave function. Okay? It's just not a wave function. This is classical field theory we're talking about for now. There's no quantum mechanics. Again, this is just some physical object which is obeying certain equations that's saying how it moves. Okay? Is that good with everybody? Any questions about this? Please.
So the phi fields have a mass in
No, the phi fields have a Lagrangian, and that Lagrangian includes certain terms, and one of those terms has a coefficient that I've called m.
Right, so
Okay. It is going to be a mass, but
it's not mass of the entire field.
no. So that's exactly why I don't want to call it mass yet. We'll quantize, we'll see exactly what it's the mass of. Now it's just a coefficient in that Lagrangian. Yeah. Other questions? No? Good. So, what I want to tell you in this lecture is more about classical field theory. And in particular, I want to focus on symmetries of classical field theories. So the first symmetry I'm going to talk about is just Lorentz symmetry, and in particular what we mean by Lorentz symmetry. The reason is that certainly if you're a particle physicist, the whole reason to do quantum field theory is to develop a relativistic version of quantum mechanics. Okay, so that's mixing quantum mechanics with special relativity to get a Lorentz invariant theory. So I want to tell you how you write down Lagrangians that describe field theories that are invariant under Lorentz transformations, so consistent with special relativity. So, Lorentz transformations. So we want to construct relativistic field theories with time and space placed on equal footing. Okay, what this really means is that the theory should be invariant under Lorentz transformations. Should be Okay, so I'm going to use the following notation for Lorentz transformations. Are people happy with this? I'm going to give some examples shortly, but is there anybody who just hasn't seen this kind of equation before? Just had GR, yeah, so it's all good. Good, so what's going on here? You take a point x, we're going to do a Lorentz transformation to move it to a point x prime. X prime is related to the original x by multiplying by this matrix. Sort of fairly abstractly, this matrix is a member of the group SO3, 1. What that means in practice is that it obeys the following equation. Sigma tau lambda mu tau mu nu. Okay, so any matrix, capital lambda, which obeys the following equation, where eta, of course, is the Minkowski metric here, is a Lorentz transformation. Okay. So just some examples. No, I think it's exactly as it is. It's really a transpose already, precisely because of the way the indices are contracted. Okay, so these, if you think about the group SON, what's the definition of SON? It's a rotation matrix which obeys R times R transpose is equal to the unit matrix. Okay, this is morally the same as that. It's lambda times lambda transpose is unit matrix, but there's unit matrices here which are really the Minkowski metric with these minus signs. Okay. Is that clear? Lost the forward eraser. Here. Cheers.
Did you get the shot, by the way?
No.
That box on the board.
Oh, great. Thanks. Okay, so you're happy with this? This is a kind of Lorentz transformation that's just a familiar rotation. Rotates us around the z-axis by an angle theta. Another example. Okay, so this is now an example of a boost along the x-axis. By the way, implicit here is the fact that this is time x, y, z. So just a boost along the x-axis, velocity v, where gamma is this usual relativistic gamma factor. You could also write this in terms of coths and cinches, if you preferred. Okay, so this is how the Lorentz transformations act on the underlying space, on Minkowski space. They take one point to another point under a transformation. But what we're really interested in is how they act on the fields that are living over this space. And mathematically, what we need is a representation of the Lorentz group on the fields. What that means in a more mundane way is you take the field and you look to see what indices are floating around that sort of tells you whether it's a scalar field or a vector field, or we'll see later a spinor field. Okay? So in this course, we're going to consider all these three different representations of the Lorentz group, scalar, vector, and spinor. But for now, we're just going to keep with the simplest one, which is a scalar field. And a scalar field basically doesn't transform under the Lorentz group, except in sort of a trivial fashion. And although it's trivial, it's really confusing. So I'm going to write it down, and then I'm going to try and explain it to you. But it's the kind of thing that's really best done in the privacy of your own home when nobody else is looking. So I'll try and explain, but you should try and figure this out for yourselves. OK, so the Lorentz transformations have a representation on fields. And for a scalar field, this is OK. So this is how it transforms. And the subtle part is the fact that this is a lambda to the -1 here and not a lambda. OK? So this is all to do with the difference between active and passive transformations. In practice, it really doesn't matter whether you're doing an active or a passive transformation and whether you put a lambda or a lambda to the -1 there, as long as you're consistent. But if it's an active transformation, it's correct to put lambda to the -1. So let me just try and explain why this is. But like I said, it's the kind of thing that everybody understands in their own way. And if I explain it in the way I understand it, it might just confuse you. So I'll do my best, and then you can go away and figure it out. Okay? So this is an active transformation that, yeah, please.
If the difference doesn't matter, and it seems clear that it doesn't matter, why? Like, is there any case in which you care? Like,
yeah, I mean, you can imagine doing some experiment where you are doing an active transformation or a passive transformation, and it really does matter. Most of what we'll be interested in here is the questions like, is this theory correct? In which case, then it really doesn't matter. But you're right. So, it's one of those subtleties that you could ignore until you maybe stumble across a situation where you have to. Okay, other questions before I attempt an explanation? Okay, so this is the way I think about it. Consider that you have a temperature field, because it's nice and physical. And the temperature field is such that it's lukewarm everywhere, but over here it's really hot. Okay, so there's just a hot patch just here. And now we do a Lorentz transformation on this temperature field, and what we're actually going to do is just a rotation. But it's an active rotation, which means I actually take the whole field and I move it. Okay, that's what's meant by an active rotation. So I had my initial field with a hot patch here, and now what I'm going to do is rotate this field so the hot patch is now over there. Okay. Initial field gets rotated to the new field, and now I want to write the new field in terms of the old field. Okay? So in particular, the new field should be such that it's hot over there. So I want the value of the new field to be hot when x is over there. But in terms of the old field, I've got to take x over there and go back to where I came from over here. And it's that going back, which is why there's a lambda to the -1. Okay, please.
You write, f over x minus a.
Yeah, it's probably exactly.
It means
the same
whether
way.
you're moving the function or the coordinates.
Yeah, exactly. Active versus passive. It's exactly. Okay. Good. Everybody's happy with that. That's amazing. Is everybody happy with that?
Passive one. That's just the passive.
So a passive one is where you're just you're not changing the field, you're just changing the labeling of the
Right.
coordinates,
So
and then there'd be a lambda there, not a
The
lambda.
coordinate axes is just the term.
Yeah, exactly.
Right.
So, so phi prime and phi are different objects. I mean, you're talking about a different field. But
I'm talking about, I have some initial field configuration, and I'm an all-powerful deity who can move the field in the entire universe. So I do that, and this is where the you will go. In some sense, doing an active transformational field is, because you've got to be big to do the whole field, right? So somehow it's not quite as intuitive as doing an active transformation in particle. Okay, good. So that's how it that's how the scalar field transforms. As I said, later we'll come across other fields that have indices here, and then those indices will also be acted on by particular matrices that are related to lambda. Okay, but we'll see them as we progress. So that's how it acts. But that's how it acts on any field. Well, we're interested in theories, particular theories, which are invariant under Lorentz transformations. So a theory is said to be Lorentz invariant whenever I'm not sure I've said this in the most concise way, but basically a theory is Lorentz invariant whenever, if you have one solution to the equations of motion, so not just any field configuration, but in particular solution, and you act on that with a Lorentz transformation, then it's still a solution. Okay? That's what we mean by a theory being Lorentz invariant. This is true. Yeah.
then that doesn't require that a T have the exact same representation, just that it gives the same, that it solves, they're both solutions and both make the same prediction. Means that they can look different out here.
Can look different. In the sense that the temperature being hot over there instead of here looks different, or?
Well, yeah, so I mean that could still be invariant even though not here.
Oh, good. No, I think this is a good question. The theory is invariant, even though particular configurations are not necessary.
Right.
So yeah, you're exactly right. In a particular configuration, you might say would break the symmetry. Temperature being hot over here breaks rotational invariance, but the theory itself is rotational.
Okay.
I mean, it's true in the universe in general. Our laws of physics are translationally invariant, but obviously this room is not translationally invariant. Okay. The final sentence, says that we can ensure that this is true, meaning that the theory is Lorentz invariant. Man, my writing sucks. But by requiring that the action S is invariant. Okay, so as a little exercise, I want you to check this in the tutorial session. So let me just write this down. So exercise. Check this. For the Lagrangian that we saw yesterday, which gives rise to the Klein-Gordon equations of motion. So what does it mean that the actions are varied? It means that for any field configuration, I can evaluate the action, and that gives me a number. Now, what I ask is that if I was to change that field configuration by a Lorentz transformation, I would get exactly the same number for that new configuration. Okay. Okay. So you should run through this, and it's a little bit subtle thinking about what you mean by the derivatives. Are they derivatives on x, or are they derivatives acting on? It's handy to call this whole object here y. And then you've got to change the measure from integration over x to integration over y, and so on. It's actually all done in detail in the notes. So if you want to sort of try it yourself, and then if you get stuck, pick it up. Okay, so it's really the kind of exercise you should do just once, because in practice, it's dead easy to see if these actions are Lorentz invariant because of this brilliant index notation. All you've got to do is make sure the mu's and the nus are contracted in some nice way, and that's enough to guarantee that it's Lorentz invariant. As long as you've not got any extra time derivatives hanging around or something, then you're fine.
Is that, what's the subscript on the first?
They're both mu.
Oh,
I've just, and this is raised with Minkowski. I guess it means okay. For example, you did a second exercise of working out the equations of motion from a Lagrangian yesterday. That Lagrangian had first order time derivatives and second order space derivatives. It's clear that that's not Lorentz invariant. The t and the x are completely different. Yeah. Okay, questions about this? Yeah.
That transformation law is only good for scalars, right?
Only good for scalars, yeah. Otherwise, there's extra indices hanging around here, and you have to get extra matrices that sit in front. And we'll come across them. Let me just give you one, because I don't want to tease you too much. So an example of a Lorentz transformation on a vector field. And you've come across this vector field A mu in Maxwell's equations. So how does A mu transform? Sorry for you guys at the back. So the x index transforms in exactly the same way, because that's this active versus passive deal. But there's also now a rotation here where the mu index gets rotated, which is what you would expect, right? This is telling you the direction that the field's pointing in, and you do the rotation, and now it's pointing in a different direction. That's all this is telling us. Yeah, if you have a bunch of mu and nu indices, it's dead easy, isn't it? Yeah. However, there are other more interesting indices you could have, spinor indices, which I think Malcolm mentioned briefly at the end of. Right. Yeah, so we'll do all that in detail.
In that case, are they the same matrix to lambda?
Yeah, so yeah, exactly. Please.
So I'm a bit confused between the inverse transformation and the Lorentz transformation, because I suppose that A subscript mu is like not a vector.
A subscript mu. This is a vector, absolutely. Yeah, it's a vector field, but it's a vector at every single point in space.
So I was expecting the component of a vector to be higher, maybe A superscript mu.
Oh, you're worried about things being up and down?
And the transformation, whether it's inverse or it's the Lorentz transformation.
Yeah, I mean, the up and down here is not as big an issue as it is in general relativity. There's minus signs that crop up. But this is right. We could probably do it for a vector field that's big here and points in that direction. And then we do this rotation over there. Okay? So now it's big over there but points in this direction. And if you figure out what that means, then this lambda to the -1 moves you back, and this lambda is the right rotation. See, I told you, privacy of your own home. It's puzzling. Yeah, please.
Sorry. So,
in, well, I guess any theory, like you'll have like these objects, like mathematical objects, like in this case, these fields, which are functions on something like R4. And you have some sort of like solution condition that says like which things are like physical solutions and which aren't.
We have an equation of motion which
Yeah. Well, I mean,
classical solutions should
yeah.
solve.
Of course, I mean, in this case, you actually don't have an equation, right? Because your condition is that it's a local minimum of the action.
That gives rise to if I give you an action, you
Right.
get a...
But I mean, it's not equivalent to the Euler-Lagrange equation because you could have, like, you can have maxima that are also solve the Euler-Lagrange equation, for example.
Oh, sorry, so the correct condition is not that it's a minimum, it's that it's an extremum.
Oh, really?
Yeah.
Anyway.
Sorry, this principle of least action,
Yeah.
complete misnomer.
Yeah.
It's never a maximum, it's nearly always a saddle point.
Yeah. Really? Oh, that's weird. Okay. Anyway. So the point is like, so typically like you do these transformations and the equation of motion stays the same and the mathematical objects, like in this case the functions from Rn to R or whatever change. And
Yeah.
so Lorentz invariance means that it's invariant under the solutions. And you can, I assume there's also an equivalent picture where the objects stay the same in the equation of motion, or I'm sorry, yeah, the equation of motion changes when you do transformations.
Yeah, I think that's right. Other questions? Okay. Good. So, now we're going to carry on thinking about symmetries. So we've set up the scene that we're primarily going to be interested in Lagrangians, which are, or theories which are Lorentz invariant. But now what we want to do is think about more general symmetries. And in particular, this beautiful result, which you've probably seen in classical mechanics, about the relationship between symmetries and conserved quantities. So this is Noether's theorem. Is there anybody here who hasn't seen Noether's theorem in classical mechanics? Okay, good. So, symmetries and Noether's theorem. Okay, so if anything, I would say that in field theory, the role of Noether's theorem is even more important than it is in classical mechanics. So certainly the amount of different symmetries you can have in field theories are much greater. So you can have standard things like translational invariance and Lorentz invariance, but there's also various internal symmetries that you can have. There's gauge symmetries, which are very important in the standard model. There's things like supersymmetries, which you'll probably get to, I don't know, maybe after Christmas. And each of these comes with a conserved object. So what I'd like to do here is tell you the statement of Noether's theorem, explain why it's important, prove it, and then give you a bunch of examples for the rest of the class. Okay, so Noether's theorem is the following. And it's slightly different for a field theory than for particle mechanics. So it's that every continuous symmetry of the Lagrangian gives rise to a conserved current. Okay, so in particle mechanics, this would be conserved quantity. Here it's slightly different. It's a conserved current. So meaning of a conserved current? Well, it's that when the equations of motion hold, then the current obeys the following equation. Which is equivalent to this. Sorry, say again? I guess I'd be partial, yeah. Yeah, actually that's important, yeah. No, the mu and the mu are both up, so this just means sum over it, and so, you know, as long as this is defined with the I up, it's good.
Sorry.
Yeah. Other questions? Okay, so let me just walk you through some of the consequences of this kind of current equation. So the first thing to say is that if we have an equation like this, we do have a conserved quantity. So a conserved current implies the existence of a conserved quantity, which is usually called a charge. All you do is you take the zeroth component of the current, you integrate it over all of space, but not of time, and you're left with something which doesn't change in time. Okay, Callum.
Symmetry of the Lagrangian. Do you mean Lagrangian or action?
What I really mean is action, and this will become clearer later. I mean symmetry of the Lagrangian, but then there's a caveat about total derivatives. And that is, we'll get to this in the example.
Okay.
So to see that this is true, let's just do the obvious thing and take the time derivative. Okay, we take the time derivative, we use the current equation to replace the time derivative of j with the spatial derivative of j, but this is now just a total derivative. So as long as there's nothing escaping at the boundary, yeah, please.
So is this only for scalar fields? Like, would the j be a different kind of object if fields are fields?
No, j is always going to be a vector, regardless of what field configuration is true. This holds for any Lagrangian of any field. Other questions?
Can we assume in general that J will go to 0 as x goes to infinity?
Yes, apart from the situations where it doesn't. You know, this will happen a lot in field theory. I'm going to assume certain things, and it could be that later you'll have to replace this with, there'll be caveats to everything else. Okay, so we have a conserved quantity. We can calculate this in Q. Again, we've got to be some all-seeing omniscient being to do that, because we integrate over all of space to get Q. So you've got to count up everything in the universe, and then you know that at some later time that thing's going to remain unchanged. Okay? But there's actually something more powerful about this current equation, which tells you that charge is conserved locally as well. Okay? Now, that doesn't mean that the charge in this little box is going to remain the same, because nothing could happen then. But what it means is that if there's some charge in a little box, if it's going to leave that box, it's got to leave through the sides. It's not just going to suddenly disappear and appear over here. Okay? So we can just see this very easily. Is stronger the charge is conserved locally. So to see this, consider some fixed volume in space that I'll call V, and define QV just to be the integral over that volume. Of the 0th component of the current. So if I just repeat this analysis, that's on this board here, and what I get is that the variation of the charge in this volume is equal to grad of J integrated over this volume. Again, it's a boundary term, and the fact it's a boundary term means that if this is going to change, which it can, it's only going to change by something flowing out the side of the box. Okay, so you write the change of Q as the integral over the boundary of the box, which I've called A, J dotted with ds. Okay? Okay, so that's as good as you're going to get for some local conserved charge. You don't want that something in a given box is just going to stick, it's just going to stay there because you can make that box arbitrarily small, and then nothing's going to happen. So things can move, but things have to move locally for this conserved charge. Okay. Okay, so the next step is to prove Noether's theorem, but are there any questions before I do that? Please.
T is basically that statement, right?
Yeah, absolutely. Yeah, this is just sort of having that out, integral equations sort of differential. Okay, so let's prove Noether's theorem. And it's the same proof as sorry.
So when you write like del A, J, A, is this the contraction of the derivative of A? Or I'm sorry. Can you think of the contraction of like del A, J, B?
Del A, J.
On its two indices.
What was del A? So you mean this thing here?
Or no, you wrote at the very beginning del A, J, A equals 0.
Del A.
Mu, yeah, it's just
Del mu.
Huh? Oh,
Yeah.
okay.
This.
Yeah.
Yeah. So this is summing over these indices,
Right.
time derivative of J0 plus spatial derivative of Ji.
Okay.
Other questions? Okay, let's prove this. So the first thing we'll do is we're going to take our symmetry, something like a rotational symmetry moving from here to here, but we're going to work infinitesimally. Okay, so we're just going to consider a little tiny rotation. There was an important word in the statement of Noether's theorem, which was that for any continuous symmetry, we get this conserved current. So that's where the continuous comes in. It makes sense to talk about a little tiny infinitesimal piece. For example, parity symmetry. You know, you look at yourself in a mirror and physics is roughly the same. That's not a continuous symmetry. It doesn't give rise to a current because you can't sort of flip yourself over a little bit. You need this sense of continuity. Please.
Is there an analogous theorem for discrete?
And the symmetries are still powerful, but much less. You could say, for example, that a particular quantity picks up a minus sign under parity or doesn't pick up a minus sign. Things like that have to match on the inside of the equation, but certainly no concern. Other questions? Okay, so we'll work infinitesimally. And again, this is where we're making use of that statement of a continuous symmetry. And sorry. Okay, so we take an arbitrary collection of fields. They're going to translate to some under the symmetry to some new collection of fields. But because this is an infinitesimal symmetry, it's going to be fairly close to where we started. Okay, so this is the small little change of the field. I'm not specifying anything about it, just that there is a change of the field at order epsilon. There'll be higher order terms, epsilon squared, and so on. We'll just ignore them. Okay, so let me just now define really what I meant by a symmetry, which I only sort of did in passing before. What I mean is that if I take the fields, any fields at all, doesn't have to solve the equations of motion in particular, and I shift them by this amount, then the Lagrangian density doesn't change at all. Okay, it's the same function, the Lagrangian density. Callum raised a caveat earlier. We're going to weaken this requirement shortly, but for now, let's just assume this. Okay. Okay, so now comes sort of the little bit of gymnastics. So consider making an arbitrary transformation. So this isn't necessarily the particular transformation that's a symmetry. This is that you've got some field, and you just vary it in any old way that you see fit. Okay, so this is any transformation that you like. Well, how does the action change? We did these calculations yesterday when deriving the Euler-Lagrange equations. The action depends on phi and the derivative of phi. So the change in, the Lagrangian depends on phi and the derivative of phi. So the change in the Lagrangian has two pieces, one where phi changes, one where the derivative of phi changes. And then we sort of integrate by parts, except that we're not integrating. So we're just sort of rewriting things. Okay, so is this clear? It's exactly the same step that we were doing deriving the Euler-Lagrange equations. So let's just remember, how do we get the Euler-Lagrange equations? We ask that the change in the action is 0. The action is extremized. When we do the Euler-Lagrange equations, we insist that this term vanishes because there's an integral here, and that this vanishes at the ends. And that leaves us with the equations of motion have to vanish. Here we're doing something different, though. We're not going to insist that this term vanishes. We haven't imposed any requirements that at any points at all the symmetry shouldn't act. Okay, the symmetry is going to the field configuration everywhere. Instead, we're going to reverse the logic. Remember, Nernst's theorem said that when the equations of motion hold, then there's a conserved current. Okay? So we assume the equations of motion hold, which means we lose this term immediately. Okay. So when the equations of motion hold, then for any variation, the change in the action is always of this form. It's always a total derivative. Okay, is that clear? So we have we have a field configuration that we're changing everywhere. And if that field equation happened to obey the equations of motion, the change of the action is of this form.
You have a field where the equations of motion didn't hold?
Again, if you're God, you just set one up.
Okay, so you just like write down a field and say it doesn't obey the...
Yeah, any arbitrary field, say how it evolves in time. Chances are, if you were to write down any arbitrary field configuration, it's not going to obey the equation.
But like those fields wouldn't have anything to do with quantum field theory or physics?
They would.
Okay.
In fact, in the interesting parts of quantum field theory, they're actually the ones that are important. Again, we'll get there.
Okay. So, are we using script L for the Lagrangian or for the total action?
Script L is the Lagrangian density. It's the thing that you integrate over all of space and time to get the action.
Okay.
Okay, so we have some field configuration. If that field configuration obeys the equations of motion, the Lagrangian density changes in the following way under any arbitrary transformation. Okay? But now, suppose that the transformation we're considering, just make sure I got this right. Oh, we're good. Suppose the transformation we're considering is the symmetry. Okay, so when the equations of motion hold, this is the change of the Lagrangian for any transformation. But if that transformation is a symmetry, by definition, the Lagrangian doesn't change. In which case, this thing here has to vanish when this is the particular transformation, which is a symmetry. Okay? That means that we've got d mu of something, which we'll call j mu is equal to 0, where j mu is this object in brackets here. Okay? This proof of Nernst's theorem is does something very unusual for proofs in mathematics. It's usual that you have a proof in mathematics that tells you the existence of something, the existence of a current in this case. This does much more. It tells you the existence of a current, and it tells you what it is. This is really why it's so powerful. You actually get to construct the current from this proof. Please.
Why does the Lagrangian density have to be 0 everywhere?
That's the definition of a symmetry. I take any configuration,
I thought so.
I change it by a symmetry, and the Lagrange density stays the same.
Why can't you have a symmetry which changes the action everywhere, or changes the Lagrangian density everywhere, but does not change the total actions?
Changes the Lagrangian density everywhere, but doesn't change the...
On the left part, it increases the Lagrangian density. On the right part, it decreases the Lagrangian density. Oh, because you can always...
No, because it's got to be true for any field configuration.
Okay.
Right, so I
Right, yeah,
think
okay.
you just can't do it. You could maybe cook it up for one, but in general, that's just not
Where did you use the epsilon as small?
when I was writing writing the initial part, when I do the rotation.
Well, that's when you said epsilon was small, but where did we wonder?
But basically, it's everywhere. The fact that I've linearized the transformation. There's delta L's everywhere,
Got it.
zero.
Okay.
You can go through it for for simple examples, you can go through for the global transformation. Even in particle mechanics, I seem to remember when I was teaching it, if you do full sort of finite rotations in particle mechanics, even that's a real pain in the arse to get the conserved angular momentum. So even there, especially, you can do it.
Well, I was just, it was clear to me that we had assumed epsilon to be small, but just I didn't see immediately where we had.
Everywhere. Delta L is equal to this. It's just running through. There was a question.
Yeah, I was just wondering why you left out this.
Oh, I put an epsilon here, but this is just some constant. So okay, J mu equals epsilon this is conserved. Let me just get rid of the epsilon. It's still something which obeys this. So there's an epsilon sitting outside here.
Is there a clear relationship between this and Killing vectors?
There's almost certainly a relationship. Yeah. What I'm going to do now is tell you about the Killing vectors of Minkowski space and what conserved quantities we get out of them. So if you had some general background, you would again get some conserved quantity from Killing vectors for a field living on that background.
Is there an implicit summation on A?
Yeah, there's an implicit summation on A. That's right.
Okay.
And here as well. All the fields that are involved in the C. Do you have a question?
So why does it mean that we can neglect the issue of adding a small epsilon, the field varying with a very small epsilon, instead of just putting epsilon delta phi, just put a delta phi? Because you see that I'm not
And
using.
if I'd have assumed that this was just small by definition, there wouldn't have been an epsilon, but I just sort of wanted to make it clear. I was working infinitesimally though, and whatever I put here has to be the infinitesimal. I'm going to set an exercise on this, and you'll see. We'll get to the end. There'll be epsilons, but strip them off. We can see more clearly that when we get, because we can actually construct this, we have specific examples, we have it in front of us, we can just check that the equations of motion indeed obey this. So we'll do these exercises. Sure. Other questions?
It's epsilon is independent of space.
Yeah, absolutely. It's just a constant. It's important. Okay, there's a slight generalization that Callum brought up earlier. So let me just mention this. So slight So we can weaken what we require for a symmetry. Okay, so suppose that I had a particular symmetry that I act on the fields with, and I find that actually the Lagrangian didn't stay the same, but it changed by a derivative of some function f mu. Okay, this is what Callum brought up earlier, because this means that the action, which is the integration over all of space of this, will be invariant because the change is a total derivative, which will just vanish. Yeah, I'm going to assume things like that throughout. Yeah, and there are particularly interesting field configurations where things don't die off at infinity. They're called solitons, and they play an important role in condensed matter in particle physics. And then you have to revisit some of these issues in that context. You sometimes get extra terms to conserved quantities, things like this. Okay, anyway, if this is true, it's clear that we can just take the proof through, because now delta L is still equal to this, but the symmetry requires that it's equal to this, which means that we can still construct a conserved current. It's the thing we had before, but this is equal to d mu f mu. So if I just subtract off the d mu f mu, then I've still got a conserved current. Sorry. Yeah. Yeah, I have a feeling I'm not going to be completely consistent about epsilons appearing and disappearing from the equations. So we'll see in the next examples.
Yeah. It's not immediately clear to me why we can weaken our requirement of symmetry to this.
Oh, so what I wanted was the following. I wanted to say that given a symmetry, where I'm going to define a symmetry in however way I want, but let me, for example, define it in this way, then if the equations of motion are obeyed, I can construct a J mu which satisfies d mu J mu. Okay. So what I had before is that
I mean, I see how the math comes out, but I don't know why.
Why this is something.
Why that is something significant.
Oh, it's because of what Callum said. That I'm not asking that the Lagrangian is invariant, but I am asking that the action is invariant. So there's a one-line way of saying action is invariant on this symmetry.
So this is sort of related back to my previous questions. If you had a field that didn't obey equations of motion, what does the Lagrangian mean?
Oh, it's a function of the field configuration. So for any field you can plug it into the Lagrangian and get a new function. You can then integrate that function over space and get a number, the action.
Okay, but is it good for anything if you don't have it, if it doesn't give you equations?
Yeah, in quantum theory it's extremely important. Let me just go ahead if you've asked the question twice. This is really what you're going to see in the next quantum field theory course in 3 weeks' time. Okay. But you've seen path integrals. So what's a path integral in quantum mechanics? It's where you don't just consider the particle to follow its classical trajectory from here to here, but you consider it following all trajectories weighted with e to the I times the action. So in quantum field theory, you've got to do the same thing. You've got to integrate over all possible field configurations weighted with e to the I times the action. Now, in certain cases, that integral will be dominated by something close to the classical solution to the classical equations of motion. Those cases are what we call weak coupling in quantum field theory. It's where perturbation theory works and we can do things. However, all the really interesting stuff is when that doesn't happen. When that path integral is dominated by field configurations that are a long way away from the classical equations of motion. So QCD, confinement of quarks inside the protons due to wildly varying field configurations that are close to classical. Other questions?
Sorry to expand on the tangent, but presumably then there's some analogous equation. Oh, never mind. I'll ask later when we get there.
Good. So I'm just going to push on and give you some examples about how Noether's theorem works for specific solutions. Okay. So we're going to do a bunch of examples. Okay, so remember in courses on classical particle mechanics that there's this beautiful relationship between homogeneity in time translations, and energy, the conserved quantity energy. And similarly, invariance in spatial translations and the conserved quantity that we call momentum. So there's going to be something very similar that appears here, and we're going to now derive what those quantities are. Okay. So consider. So these are the space and time coordinates, and we're just going to consider the translation by some infinitesimal amount, epsilon mu, in either space or time, one of the directions. Okay, we know how all the fields transform because it's just Taylor's expansion.
Transformation, so I expected a negative.
But the rest of my notes have the plus sign, so we may have to struggle through and fix that minus sign everywhere. Let me do this, yeah. Good. Okay, so if the Lagrangian has no explicit x dependence, okay, so the Lagrangian is also a function of x, but it's a function of x as phi is a function of x. But any function of x is going to shift in the same way. Notice that this sits in the class of the slight generalization. Under the translations, L isn't invariant, but L shifts by a total derivative. Okay. So what we're going to get is 4 conserved currents . So 4 because we've got 4 different transformations here because we're in 4-dimensional Minkowski space. This index here goes 0, 1, 2, 3. And we know exactly what they are. What they are is the following, just from reading off from Noether's theorem. So let me just walk you through the notation here. This is the current. Okay, so the mu index at the top there is the mu index that we already saw in Noether's theorem. This new index here, this new index that's new, is the thing that goes 0, 1, 2, 3, because we have 4 different currents that we're computing. Okay, but because this is a rather special current, translations in space and time, the 2 indices go over the same range. Okay, so this is just reading off the current from Noether's theorem. This was the first part, and this is what we called F mu here. And if you just look at what F mu is, it's basically the Lagrangian itself with this delta mu nu index. Okay. This is a rather special object in quantum field theory. It's got a name. It's usually written in the following way. So this obeys this equation, which is just this current equation we've already seen. And T is called the energy momentum tensor. You'll sometimes hear other names for it, the stress energy tensor, sometimes just the stress tensor. It's nearly always called T. Is there a question?
GR last week. And is this 2 the same 2 that you would see in the Einstein equation?
Not yet, but I am going to explain how the relationship is.
Okay.
Okay, so we've got 4 conserved currents, so 4 conserved quantities. Okay, so the conserved quantities are always the integral over space of the zeroth component of the current. So we've got 4 possibilities, whether the other index takes its value at 0 or whether the other index takes its value in space, I equals 1, 2, 3. So just to give you some feel for this, if we take this Lagrangian that gives rise to the Klein-Gordon equation, we plug in that expression for the stress energy tensor, T mu nu, it's given by the following. And in particular, we can now calculate the energy. And the momentum. Okay, so again, these are 2 conserved quantities associated to the entire field. Okay, nothing local, the entire field. And you can see that the nice thing has happened that usually happens in classical mechanics, which is that the minus signs that were here for the Lagrangian get flipped to plus signs, and then the energy is the sum of the kinetic energy plus the gradient energy plus the potential energy. Okay? But again, integrated over all of space, so summing this up for everywhere in the field. And similarly, the momentum is, well, it's given by the following integral. The momentum sort of, you can see from this expression, it's kind of telling you how much the field is going in that direction. Okay, so it has this, the correct field of momentum to it. Okay, any questions? Okay, so I think I'll stop in. Tomorrow, what I'm going to do is answer Callum's question, tell you how this T mu nu is related to the one that you see in general relativity. In fact, for a scalar field, this is the T mu nu that appears in general relativity. But for other fields, there's some subtleties. And then I'm going to walk you through various other examples of conserved currents in field theory. Okay.